All right. Hello, everybody. My name is Michael Prenger. I'm a PhD student at CISPA, and I'm going to present to you our paper called xOSSig, Leveraging OS Diversity to Automatically Extract Malware Code Signatures. This is joint work with my supervisor, Christian Rosso. Now, to motivate our work, what we are actually trying to achieve is that given a memory dump of an infected system, we want to attribute which malware infected the system. That is, we want to automatically create signatures to do this task. Now, if we look at existing solutions that we could possibly use for such a task is AB labels or Yarrow signatures. The problem is these are usually very sort of generic signatures, as it turns out. They are not very accurate because they mostly focus on strings and data. So if you have ever worked with Yarrow signatures, you probably know this, right? You apply it to a sample and it shows something that doesn't really make sense. It matches random data as belonging to a certain malware family or something like that. So it doesn't really work that well. Now, this by itself is a problem. You could say you just need to improve the signature, that's fine. But another problem that we find is that usually off-the-shelf signatures that you can find online, for example, are not really intended for being used with memory dumps. That's actually a big problem. In our experience, they really are intended to work with the samples, and if you try to apply them to memory dumps, they simply don't work. So we basically want a solution to overcome that. We want a solution to automatically create such signatures and that they work with memory dumps. Now, a big problem here is that we want to do this in a completely forensic setting, and therefore the analysis surface is the whole memory dump of the system. And as we will see soon, this is actually quite a challenge. Now, why is this actually a big challenge? So the problem is that if we look at a memory dump right here on the left, that is infected by a malware, it's indicated by this little red guy down here. Now, if we want to understand how we can analyze this, we have to think of the memory as memory pages, right? As you probably know, memory is allocated at a page granularity, and it makes sense to look at pages as a natural boundary of the memory dump, sort of. Now, if you think of a memory dump, it's quite big, right? It could be multiples of gigabyte on a modern system. And however, if we actually look at the footprint of the malware, we will find that only a very few pages are actually infected, right? So here we have this huge number of pages, and we have like 1, 2, 3, 4, 5 infected pages. And of course, in practice, it's even much worse. We're talking about hundreds of thousands, if not millions, of benign pages, and maybe 100 or a few dozen of infected pages. So it's really a needle in a haystack problem. So how can we actually, as a first step, understand which of the pages are actually interesting in terms of being attributed to the malware, and then we can start thinking about how we can generate a signature of those pages. But the first and the really important step is to find those pages automatically. Our idea to solve this problem is called cross-OS execution. So here I'm going to give you a very high-level overview of our approach. And later on, I'm going to refine the actual details as we have implemented it in practice. So what you can see here is a very basic pipeline of a malware analysis system. On the left-hand side, we have a set of malware samples that we want to analyze. And in the middle, we have a sandbox or sandboxes that we will use to analyze the samples. So the way it works here, we take this black sample and we execute it. Now, however, the interesting step is we execute this in 2 different machines. In particular, we execute it in a Windows XP machine and in a Windows 7 machine. Those are virtual machines with a predefined snapshot. And we execute those, and then we take the memory dump of both systems. And now we have those 2 memory dumps, and they both have infected memory pages that are infected by the same malware. Now, how do we solve the problem of actually understanding which of the pages are interesting? And as it turns out, what is a really useful way to do this in practice is that we take those 2 memory dumps and we intersect them. Now, what does that mean? I will tell you later in detail. But the basic idea is those systems are similar, but not identical. And their similarities should be mainly the memory footprint of the malware. And if we do this, the really important aspect is that, as I have said before, the Windows XP memory dump and the Windows 7 memory dump are in the order of gigabytes in size. And the actual footprint that we get by intersecting is much smaller. We're talking about a few kilobytes maybe. So the very basic motivation and observations of this idea are as follows. First of all, as I previously mentioned, most of the pages in the memory dump are really uninteresting for us. They are basically, we can basically consider them noise, right? So we have benign processes, we have services, we have kernel code, we have libraries, device drivers, and so on. They are not interesting and completely useless for us in terms of generating a signature for the malware. And the other observation is that we have two systems that are similar but compatible. In particular, this means the malware is very likely to run on both systems. First of all, because in our case we use Windows, and Windows is an ecosystem that is very well known for its backwards compatibility. And also, malware authors usually try to make sure that their malware runs on as many systems as possible for obvious reasons. And the interesting aspect here is that the forensic footprint of those operating systems is not identical. It's actually vastly different. So by intersecting the memory pages, again, we will get into the details of how this actually works. But by doing that, we can actually abstract from the background noise automatically. Now, a problem that I can already foreshadow at this point is that the two operating systems, while not being identical, they are still similar and they still share some footprints. So as is probably not really surprising, there is legacy code in Windows that will be shared between different versions. And part of our task will be to identify those similarities and abstract from them in the learning phase of our system. So here we can see a more detailed overview of how our approach actually works. This is a figure that can be found in our paper. We will, in the following slides, go into the details of every step. The way it works as a very high-level idea is on the very left-hand side, we start with malware that is executed on two different Windows versions. Then it goes to some process that we will describe in the following slides. And on the right-hand side, you can see the final result of this process, which is a fingerprint for this malware. And as I've said, we will now go into the details of every step of this procedure. Now, the first two steps of our approach are explained here. The very first step, the execution step, I think it doesn't really need that much explanation. We basically take the malware and execute it in two different virtual machines with different versions of Windows. The only thing that might be interesting to mention here is we use snapshots that we have previously created, and we execute the malware on both systems for the same amount of time. After that, we take a memory dump. A memory dump here is represented with such a grid, and each cell in the grid represents a memory page. The individual letters stand for different contents. So if two cells share the same letter, that means they have the same content. And the X suffix in some of the cells means that the page is considered executable by the operating system. So in the page tables, it has the execution bit set. And we will use this later because, as I've previously mentioned, we are interested in code signatures. Now, the next step is the unique step. In this step, we filter out all the pages that are not unique in the memory dump. To understand this, first of all, I think it's intuitive to understand that something that appears, let's say, 20 times in the memory dump, so one page appears 20 times, it's probably not characteristic for the malware. In practice, what we have seen, for example, is that it's very likely that several processes on the operating system use the same library, maybe static link, for example. And because of that, we will have the same code multiple times on the system. And that's, of course, not interesting for us, right? So it allows us basically to abstract from such noise in a very easy manner. So what you can see here is, for example, that the A page, the executable A page, is filtered out. The B page is filtered out on the top because those are all not unique in the memory dump. So A appears multiple times. Once it's executable, once not. And that's because it's filtered out. B appears multiple times, C, and so on. And all these pages are filtered out in this step. And the result of this are the memory dumps on the right-hand side. The next step is called the common step. It's also a very simple step, but it's very central and very important to our approach. In this step, we are basically abstracting from background noise of the operating systems. And the way this works is we basically only consider the memory pages that are shared in both memory dumps, and by that we filter out the pages that are not shared. which we consider the noise of the operating system. So in this case, as you can see in the first memory dump, H is not shared with the second memory dump, and J and K of the second memory dump is not shared with the first memory dump. And therefore, we consider H, J, and K noise, and we keep D, E, F, and G. And by the way, that they appear at the same offset here does not matter. D could also appear in the first position. It's just coincidence in this case. And this basically is where the strength of our approach comes in, because this automatically abstracts from noise. As I have mentioned before, the operating systems, while being different, they are still similar. And they share legacy code and data that we cannot necessarily abstract from with our intersection idea. In this step, we want to solve this problem. So what we have done so far, we have computed the unique and common pages. In this step, we want to understand which pages are characteristic. So it's basically the last step that abstracts from all the noise. And to abstract from the noise, we have a deny list. A deny list is a list of pages that we learn in a learning phase once that exactly contain this noise, these noisy pages that we cannot abstract from by intersecting. We will shortly get into how we build this deny list, but at this point we just use the deny list, and we use it in a very simple fashion. We take the memory pages of the memory dump and we remove all the pages that are contained in the deny list. So in this case, E and F are in the deny list and they are removed, and we are left with D and G, which we coin the characteristic pages of the malware that has been executed. Now, to build the deny list, we proceed as follows. The procedure is outlined here. First of all, we start with an empty list, an empty deny list in the first step, and then we do something which we call an idle execution. We basically run this whole cross-OS apparatus that I have previously described, but we do not insert a malware into the system. We just let it run without the malware for the same amount of time that we would run it with the malware, but it basically just idles. It does nothing interesting from a malware analysis point of view. Then we take the memory dump and we extract the unique common pages as before, and then we add those pages to the deny list. If we have added a new entry to the deny list, we proceed again from step 2, so we repeat the whole thing, and we repeat that until we do not have any new pages. It turns out in practice that this process terminates quite quickly, so it maybe takes like 3 or 4 iterations before we do not see any new pages. And that's mainly because we use snapshots and things are rather deterministic every time we start an operating system. So after this, we have learned the pages, we have a deny list that we can use as previously described. The final 2 steps of our approach are explained here. The first step is the code extraction step. In this step, we simply remove all pages that do not contain code. So in this case, the G page will be removed, and we are only left with the D page that will be used for the fingerprint generation, which is the last step. The fingerprint generation works by extracting n-grams. So the way it works is we use a sliding window that we slide over the D page, and we extract its n-grams. And these n-grams will then later be used for matching a memory dump. That is, we compute all the n-grams of memory dump and we intersect it with the n-grams of the generated fingerprint. And depending on the size of the intersection, we will have a match, but we will get into that later. The only important step here to mention is that for the code extraction, we use a code heuristic that disassembles the page and looks for common x86 code patterns. So for example, a push, a call, then you do a call, a test, and then a conditional jump. And depending on how many of those patterns you find, we consider a code page. The details can be found in the paper. It's important here to mention that we do not rely on page table information or OS information because we want our approach to be generic. Basically, our approach depends on nothing except for the instruction set architecture, x86, but changing that is merely an engineering effort. So after this step, we have finally a fingerprint that can be used for detecting the presence of a malware family in memory dumps. Now let's come to the evaluation of our paper. So first of all, I'm going to explain the data set and the setup that we have used. We have used the VirtualBox hypervisor, a Windows XP virtual machine, and a Windows 7 virtual machine. VirtualBox, that doesn't really matter. You can use any hypervisor you like as long as it is capable of creating a memory dump, which I guess pretty much every hypervisor can do. The only interesting part here is that we have taken great care to set up the VMs to have a rather silent memory footprint. So we have disabled as many services as possible. We have made sure that there is not really any network activity. There isn't really any new processes being spawned that much. So we have basically taken care that the systems are really silent. That basically makes, for example, generating the denial list a lot more efficient. And it also makes sure that we do not introduce any new noise. We reduce that as much as possible. We have used 70 popular malware families, such as Carbonac, Triadex, Timber, and so on. And in total, we had 197 malware samples. The full list of the families can be found in the paper. Now, this number, 197, might sound a little small, but we want to mention that we have taken great care to create a very high quality data set. So we have basically executed all those malware samples into the two VMs, Windows XP and Windows 7 VM. And we have basically babysitted all of the 394 malware executions and have made sure that the actual family really becomes active in the system. So basically, we can be sure that all the labels of all the memory dumps are 100% correct. Now, as a first step of our evaluation, we wanted to understand the family uniformity. This graph can be found in the paper, and without going into too much detail, what we actually want to know here is how many samples of a family do we need to reliably detect the whole family. So basically, this works here is on the x-axis. We have the number of samples that we can use to build a fingerprint. So for example, if we have 3 samples, we create a fingerprint as described before for each sample, and then we take a union of all those n-grams, and this is now our fingerprint for the family. And on the y-axis, we have how many n-grams we have left if we intersect this fingerprint with the n-grams of all the memory dumps of the family. So for instance, to give you an example to make this more clear, let's look at the Kilios, this red dashed line case. In this case, even if we have just one sample and we learn the fingerprint, and we intersect those n-grams with the n-grams of all Kilios memory dumps, we see that we have almost 1 million n-grams after the intersection. So that means knowing one sample is already enough. If we compare this, for example, with, let's say, this purple line, which is a NIME, one sample does not work that well. We only have very few n-grams. And if we have 2, it gets better, and 3, and of course, the more we have, the better it gets. So we can see some families are more uniform than others. And we can also see that the intersection size is vastly different, right? So for example, Kilios is very uniform. It contains almost 1 million n-grams in the intersection. But for other families, it's vastly different. For Triadex, we need to know a lot of samples because there's probably much more diversity in the Triadex family. And we need to know like 1, 2, 3, 4, 5, 6 samples to properly detect Triadex. And so on. So for other, the families are quite different in both aspects, which is important for later when we actually want to develop a mechanism to detect those families in memory dumps. Now here we have the most important part of our evaluation, where we have actually taken out an experiment to develop a mechanism to see how well we can detect the presence of a malware family in a memory dump. The way this works is as follows. For each malware family, we have created an equal split of the malware samples. So for example, in the case of Carbonac, we have used 5 malware samples for learning the fingerprint, and then the memory dumps of the 5 remaining samples for matching the fingerprint. And you can see here in the corresponding cell that on average 5.51% of the fingerprint have matched, and the average entropy of the matching engrams was 4.26. And you can see in the other cases, so in the case of Carbonac, only Carbonac matched on average really well. In the other cases, it did not match that well. It's not really 0%, but we excluded a result from the table if the average was below 0.01%, just for readability reasons. And based on those results, we have then evaluated optimal thresholds for both the average matching portion of memory dumps and also for the average entropy. As we can see, on average, it works out as expected. So a fingerprint for a family on average matches really well, only with its own family. In the case of foreign, we have one false positive. That is explained in detail in the paper why we have that false positive, just to say that our approach, of course, also has limitations. And if we proceed with the remaining family members, so the table is split in two for readability reasons, we can see that it also worked pretty well for others. We did not get all true positives in the case of Nijmegen, and also Virat also had some cases where it didn't work that well. But for all those cases, we actually did case studies with quite some interesting insights that can all be found in the paper. In total, the result of this evaluation is that our approach gives a true positive rate of 93% and a false positive rate of 0.15%, which shows the feasibility of our approach in practice. Now let's talk about the limitations of our approach. So we make some assumptions that could be challenged by some people. So, for example, what could happen is that a malware behaves differently on two operating systems and has different memory footprints, so the intersection won't really work. That can happen. It mainly applies to droppers. So a dropper might drop a different campaign on Windows XP than it does on Windows 7, where it might drop something randomly for other reasons that we cannot know in advance. So in this case, of course, our approach won't work. Another problem is that we assume that the malware is always present in memory, which might not necessarily be the case. For example, if you think of ransomware, so there are ransomwares that just change the desktop background once and then they exit and they leave the memory, and the desktop background then contains the ransom message. So in this case, if there is no memory footprint of the malware, our system doesn't work. However, the infected memory dump will also not really have that information in memory because, for example, in the case of the changed desktop picture, it will be on the disk, right? So yeah, it cannot work in that case. Then there are also very complex packing schemes or obfuscation schemes that we cannot deal with. So for example, if you have something like VM obfuscation, or you have packing schemes where functions are lazily packed and unpacked on demand. So whenever you need a function, you unpack it, and when you don't need the function, you pack it again. That's really out of scope for us. That doesn't really work because at the time we take the memory dump, we can only see what is unpacked at that moment, and that can be different on both systems. So these are also out of scope. In the reviews, we have also seen that some people mentioned alternative instruction set architectures. That's not really a limitation because adding support for a new instruction set architecture is merely an engineering effort. So for example, if you want net bytecode, you just need to add a disassembler for net bytecode and write a new code heuristic. So that works. Now to conclude, I have presented xOSSig with the cross-OS execution, which is the first methodology to exploit OS diversity for malware analysis. It works in a purely forensic setting. It is completely automatic, and most importantly, it is also completely independent of any OS or hardware idiosyncrasies. In particular, I don't see why this wouldn't also work for Linux, for example, or any other operating system. We have seen a promising evaluation that shows that our approach is actually feasible in practice with a 93% true positive rate and a 0.15% false positive rate. So that's it for my talk. You can see again the overview of how our system works, and I'd be happy to answer questions.